how can you get a negative work? In other words, how can you decrease the energy? And one example of that is with friction. Okay? So with friction, recall was coefficient times normal. Okay? This is a resistive force. Okay? And when you think about an object sliding, so it's moving this way with a speed, and then sometime later, it has a new speed that's less. That's because the surface is rough and has friction. Now, as the object slides, what would you notice about the surface? Well, you can do that experiment now. Take your hands and slide your hands together as if they're cold, right? Why do you slide them together? Because when you create the friction, you start generating heat on that surface. Right? Temperature increases. Okay? So that means there's some exchange of heat energy. Okay? And we define this then as a change in thermal energy. Okay? And because we know that friction is a force doing work, it follows that a force like friction, so a work because of friction, changes our thermal energy. And so when I push a box and I'm giving it energy, right? So let's say I am pushing on a box for 2 meters, and as a result, I've given the box 10 joules of energy. Well, once it starts to slide along that surface, okay, so I've stopped pushing it, and I slide along that surface, eventually it'll stop. And once it stops, well, where did all the energy go? Where did all those joules of energy that I gave the box go? And the answer is friction did work, and it converted all that energy into heat or thermal energy. And that is the one way we lose energy in a system. All right, so a new form of energy we're going to talk about is thermal energy. So in thermal energy, let's look at an example. We've got a box of mass M being pulled with a force F, but the overall velocity is constant. Okay, so what does that mean? It means that if the speed v is constant, then there is no change in kinetic energy. Okay, which therefore means there is absolutely no net work being done on the object. Okay, so even though there's no net work, the force we're using that we're applying to the box is moving the box, and therefore F, the applied force, is doing work. So that means that if F is doing work, mainly a positive work, there must be another force. And we know that that force must be friction. And that force must be doing negative work. Okay? And it's doing the exact same amount because we know the net work has to be 0. Now, to go a little more detailed about this, we know that our applied force F must be equal to friction, right? Now, why is that? Well, because our speed is constant. And remember, if speed is constant, net force must be 0. Okay, so back to this idea of work. So again, F does positive work, friction must do negative work in the same amount, such that the total work is 0. So conceptually, what does this mean? It means that the energy given to the box by the force F is taken away by friction. Okay? And what kind of energy does friction produce? Okay? Well, we define this kind of energy as thermal energy. Okay? Now, understand this. There is a lot more to thermal energy than I'm going to explain here. because we don't talk about things like heat and temperature in this class. The basic idea is thermal energy is not just what you feel as the warmth, like if you take your hands and rub them together, you create friction, which generates heat. And heat is a transfer of energy. And when you see thermal energy, it's not necessarily meaning, well, it's just because this feels hot, there must be thermal energy. There's a lot more going on at the molecular level. And when you read through the chapter on energy and you get to the thermal energy part, read through that part because it talks about that intermolecular workings. But really for this class, we care more about holistic, big picture views. And so understanding the molecular nature is not vital, but it is interesting and it's especially helpful to connect the dots. Okay, so again, I recommend that when you go through this chapter, when you get to that section on thermal energy, read through a little bit. Now we've got one final unit here, or part to the unit here, and that is power. Okay, and we define power as the rate that energy is transformed in your system. So we define it as the change in the amount of energy in the system divided by how much time it took to do the transformation. The units are in joules per second, which we can shorthand to what we call watts. Okay, you may have heard this term before, like in light bulbs, because that's really all light bulbs do. They're converting electrical energy and transforming it into another form over a certain amount of time. And the quicker they can do that, the more they can transfer that energy in a smaller amount of time. The larger the wattage, the brighter the bulb. Okay, so, but that's what watts really is. It's how much energy, joules per second. Now you can also look at look at energy you can look at power a different way. We can look at power as the rate that energy is transferred. Okay, focus on the two differences. First one is the rate energy is transformed. The second one is the rate energy is transferred. Well, work is what transfers the energy. So we define that way of pretty much the same expression, but this time it's work over time. Now, I'm not giving you these two expressions to say that they're different. They are, but they're not. Okay, it just depends on what we're talking about in the problem. Are we talking about how kinetic energy changed to potential energy? Well, that's an energy transformation. How much energy changed in that much time? If we're talking about doing work on an object, then we're doing how much transferred. So it just depends on the scenario of the question. Now, the way that I like to explain how we define power or how to think about power is through an example. So imagine a scenario where we have a 1 kilogram box at the bottom of an incline, okay, where the upper ledge to that incline is 10 meters high. Okay? And we've got two people that are going to each lift their own box the same distance. Now, the person on the left gets the box to the top of that incline in 20 seconds. The person on the right gets it up there in 100 seconds. So first we can ask, well, how much work does each one do? Well, work is force times the displacement. So if the displacement is up, what force are we fighting against to go up? Well, that's gravity, mg. So 1 kilogram times gravity, which is about 10, times the displacement of 10 tells us we did a work of 100 joules. Okay, so what about the person on the right? Well, it's the same box, and it's going the same height, so they actually do the same amount of work, 100 joules. So what's different about them? They both did the same amount of work. However, the person on the left did it in 20 seconds. That means they exerted 5 watts of power to lift that box 10 meters. Whereas the person on the right only exerted 1 watt of power because it took 5 times as long to get up there. Okay? So that's the idea of power. Now another way we can define power is the rate that energy, okay, is transferred to an object. So again, we're adding a little bit more to that second definition of power. It's the rate of energy is transferred to an object. So to understand that one, it's really just a mathematical variation of what we're already given. Again, you would use it depending on the problem. But for this one, we're talking about how much force do you apply on an object that's moving. So it's the applied force times the speed the object's moving tells us the rate at which we're giving energy to that object moving at that speed. And it's still power, so it's still in watts.